In the last lecture, we discussed examples of motion where there is energy dissipation. That is, cases where the system could lose kinetic energy irreversibly. Once the system lost kinetic energy, the system could never gain the energy all back as kinetic energy again. Let's emphasize right up front that this dissipated energy doesn't just disappear. We know that can't happen because our energy principle says it can't. And we believe the energy principle because countless experiments have shown that it's always true. In this case, the energy principle tells us that any negative change in one energy, like a negative delta K, change in kinetic energy, lost kinetic energy, must show up either as a gain in another type of energy in the system or as energy transferred out of the system, or both at the same time. Here we'll focus on a new type of energy change in the system, a change in thermal energy that often shows up when we have energy dissipation. To understand what thermal energy is, let's start by bringing to mind our microscopic picture of solid matter. Remember, we discussed how we could think of a solid as consisting of balls linked together by springs. In this ball and spring model, the balls represent the atoms or molecules, and the springs represent the chemical bonds. Now we might be picturing this in a static way. Everything is motionless unless we do something like stretch or compress the material. Actually, that's not realistic. In fact, the atoms and molecules in a typical solid are in constant motion, meaning these atoms typically have kinetic energy at the microscopic scale. And at the same time, the chemical bonds would be stretching and compressing, which we can think of as the springs in our model constantly compressing and stretching. This means that there would be potential energy in the system at a microscopic scale too. Moreover, this microscopic kinetic and potential energy would have a disorganized character. The motion of the atoms and the stretching and compressing of bonds would seem to be occurring with a good deal of randomness. This disordered kinetic and potential energy at the microscopic scale is what we call thermal energy. So what happens often when we have energy dissipation in a motion problem? The loss of the energy at the macroscopic scale, say as a negative change in kinetic energy, shows up as an increase, a positive change in the thermal energy. It's this disordered random character of microscopic motion that makes it impossible to extract out all of the thermal energy change and put it back into the macroscopic motion as, say, the system's kinetic energy. At the macroscopic scale, we typically can't see changes in thermal energy. To see the effects of thermal energy change, we would need a super-duper microscope that would allow us to look at individual molecules at the atomic scale. If we had such a device, we would see that an increase of thermal energy would show up as the atoms moving at random with larger speeds, on average, and the bonds would, on average, appear to be stretched and compressed more. However, we typically don't have such a super-duper microscope. How then can we measure something that tells us about thermal energy? Fortunately, there is an easy way to measure thermal energy. We can do this by measuring the temperature. The temperature is a measure of the average thermal energy of an object. An increase in thermal energy of an object is typically associated with an increase in the temperature of the object. For example, if you give a box a shove across the floor, the box starts out with some kinetic energy but ends up with zero kinetic energy. Delta K is negative. This energy would show up as an increase of thermal energy in both the box and the floor, and we could measure that as an increase in the temperature of the box and the floor. Now, the exact relationship between thermal energy and temperature depends on the properties of the object. For our purposes, we are interested in relating the change in thermal energy, delta E thermal, of an object to the temperature change, delta T, of that same object. This connection is described by this expression, where delta T is the temperature change expressed in SI units of Kelvin, or equivalently in degrees Celsius. The thermal energy change, delta E thermal, is in joules. M is the mass of our object, and C represents another physical property of the object, the specific heat capacity. The specific heat capacity depends on the material that the object is made of and tells us that for a unit quantity of mass, how much thermal energy change occurs for each degree of temperature change. So, for example, say our object is a wire that is made of copper, then the specific heat capacity of copper is 0.38 joules per Kelvin per gram, meaning that for each gram of the copper wire, a change of 0.38 joules of thermal energy occurs for each 1 Kelvin change in temperature. Note that the units for specific heat are not completely SI here. The mass unit here is the gram, so take care to express the mass m in the same units when you are working with thermal energy problems involving the specific heat capacity given in these units. Let's practice this on this clicker question. Here's how to solve this problem. Our system here has 1,000 grams of mass, the mass of the water. We're told that the thermal energy has increased by 7,000 joules. We're also given the specific heat capacity of water, 4.2 joules per Kelvin per gram. So the unknown here is the change in temperature. Rearranging this expression and solving for delta T, we find the temperature increase is 1.7 Kelvin. Now that we have some idea of what thermal energy is, we are in a position to discuss a new energy transfer process that involves thermal energy. We'll take up that topic in our next lecture.